Welcome to General Chemistry 1. In this chapter 2, our main focus will be on the early atomic theories, the modern atomic theories. We'll also be talking about specific topics such as subatomic particles, such as proton, neutron, electrons. Also, we'll be talking about isotopes, how ions are formed, a little bit overview of the period table, and finally the second most important topic is the nomenclature of molecular and ionic compounds. Okay, let's start out with early atomic theories. Around 400 BC, the Mercurius proposed that matter was composed of indivisible particles called atoms. Later, John Dalton's around 1806, John Dalton's formalized the atomic theory and also defined that hydrogen is the smallest atoms, and he with the one atomic mass unit, and he defined everything else based on hydrogens. On our modern theory, we base on carbon, which is the most important element. Okay, simply because carbon show up in pretty much all organic matters. Okay, when you combust or you burn everything down, you see the carbon, the black residues before it keep burning into carbon dioxide, which is colorless. Okay. And here's the key concept of John Dalton's atomic theories. Each element is composed of tiny, indivisible particles called atoms. Second, in the chemical reactions, atoms of one element cannot change into atom of another element. They're only rearrangement of atom attachments. So when you do a chemical reaction, basically you rearrange the way atoms are bonded. Okay, for example, atom A is bonded to atom B, and then react with CD, and then you can rearrange to A bonded to C, or so on and so forth. 3, all atoms of a given element have the same mass and other properties that distinguish them from atoms of other elements. In other words, if you take an atoms of gold and you compare with an atoms of copper, they are different because they come from different elements. Okay, in terms of all the physical and chemical properties. And the last one of the John Dalton theory is in order to form compounds, atoms combine together in a simple whole number ratio to form molecules of compounds. Remember, you have a compound such as water. You have 2 hydrogen atoms combined with 1 oxygen atom to form a water compound. And if you have a sample of water, it consists of many, many molecules of water. Okay, so that's the essential idea of item number 4 of John Dalton theory. All right, all that's a very good foundation for the modern theory, but in the modern theory, scientists went further into the structure of the atoms. It's all started out with J.J. Thomson using cathode ray tubes. At the end of this handout, you see the picture of cathode ray tubes. So let me scroll it all the way down. The cathode ray tube, that's the picture of cathode ray tubes. And with a filament that sent out the beam, and J.J. Thomson discovered that's the beam of electrons. Okay, and you can read more about it in the textbook, how he performed the experiment. Okay, so J.J. Thomson discovered electron, and here we are, using the cathode ray tubes, and he did a lot of work and discovered that the charge to mass ratio of each particle was negative 1.76 10 to the 8 coulomb per gram. Okay, that's a lot. A ram of electron is a lot. Okay, so that's why you get a lot of charge. The Notice that the for hydrogen is positive. Okay, so electrons are negative, and hydrogen is hydrogen ion is the proton. When you kick out the electron, it's positive. It's 9.58 10 to the 4 coulomb per gram. Okay, of the hydrogen ion. The Thomson also proposed the plum pudding model of the atom, and you can also search about that. Basically, Thomson said that an atom is a sphere composed of all these particles, negative electron and positive particle that distributed evenly in an atoms. Okay, so after the discovery of the electrons, from Thomson's, Millikan's did a very good experiment, and at the end of this handout you see the picture of the oil drop experiment from Millikan's. So basically he sprayed the oil into a chamber and electrons stick to that, okay, and by careful measurements and comparing different droplets of the oil, he estimated an electron. Pretty awesome. One electron has a charge of a negative 1.6 10 to the minus 19 coulombs. C is coulomb, is the units of charge. And an estimated mass of 9.1 10 to the minus 28 gram. This is really tiny. And notice that the each proton has a charge of positive, exactly opposite with electron, and it's a mass really small too. But it's about 1,800 times bigger than the electrons. Okay, 1.673 10 to the minus 24, and neutron has no charge, but it's a mass similar to a proton. So that's why when you make it simple, you make proton 1, neutron is also about 1, and then electron you can ignore the mass. So that's why we say that the mass of electron is 0, but the actual mass is not 0. Okay, so but now you know where to look them up. Okay, the Rutherford was working with Thomson's, and Rutherford was trying to prove Thomson's theory, the plum pudding. Turns out he discovered something new. So what happened was Rutherford used the Goldfoy experiment, and that's the Millikan experiment, the oil drop. Rutherford used the Goldfoy experiment, and it's a thin piece of gold, and he sent in the alpha radiation, and it turns out most of the alpha rays went right through, so there must be gaps, between all these particles. That's why he proposed that. It turns out an atom is not a solid piece. An atom is just mostly empty space. Only the center of an atom is solid, and he called that the nucleus. That's how he discovered the nucleus of an atom. Surrounding the nucleus is just a cloud of electrons, and that's pretty much empty space. Remember, electrons are tiny, so that's the only way UV alpha ray can go right through. Okay, could go right through. Okay, so that's pretty good discovery of the structure of atoms. Okay, and then later we got the modern atomic theory. If you look at any periodic table, you will see two numbers. Like here, this is an example. You see two numbers, and here I've put in mercury. On the regular periodic table, the atomic mass is usually on the bottom, but here I put it on the top, and this is the old-fashioned way, which is great. But anyway, the bigger number is the atomic mass, the smaller one is the atomic numbers. Okay, atomic number is the same as number of proton. Atomic mass is number of proton plus the number of neutron. All right. Now remember, on the periodic table, you don't see whole numbers, only the artificial one, okay, or the man-made one, the one made in the lab. But you see numbers like 202.529 or whatever, okay. That's because in the periodic table is the atomic mass is the average, the weight average of all the isotopes, okay. Isotopes are different atoms but they're from the same elements, and they have different They only have different number of neutrons. Everything else the same. The proton and neutrons, electrons are the same. Okay, so that's why you see all these decimal numbers for the atomic mass. However, the atomic number is always fixed numbers. So when you talk about atomic number 80, it has to be mercury. Okay, so that's atomic number identify the elements so, as much as the symbol does. Okay, or you say Hg, you know it's mercury. Okay. And here's the formula of how to calculate the weighted average, the average atomic mass of an element based on many isotopes. All right, for ions, remember electrons are the particle that moving around the nucleus, so it's outside the nucleus. So it's possible for an atom to lose one or more electrons or gains or incoming electron, gains one or more electrons. And that's how ions are generated, okay? When an atom loses electron, it becomes a positive ion called cation, and when it gains electrons, it becomes an anion that's called anion, is negative ions, okay? The on the periodic table, the mass numbers, if you see the decimal, the average mass number on the periodic table, that's also known as atomic weight. So if you look up mercury, is mercury right here is 200 point with tiny 592, something like that. Okay, that's the average, and we call that atomic weight. Okay, if you want to use the mass numbers, then we have to round that off, or we're given the isotopes, which is the exact counts. Okay. But other than that, we can use that as the atomic weight. And that's good for calculation purposes. On the periodic table, also be familiar with droop. Droop goes by vertically. Those are the columns. Droop 1, droop 2. Droop 1 is known as alkaline metals. Droop 2 is known as alkaline earth metal. And then you have droop 3 all the way to 12. Also underneath that, I like this table because it has the old fashioned way to name them with Roman numerals and the letters. Okay, droop 3 to 12 are known as transition metals. They have multiple, most of them can form multiple charges, various ions with various charges. And then you have droop 13, 14, 15, droop 16 is called chalcogens, droop 17 is called halogens, and droop 18 is called noble gases. Okay, so those are specialty names. And then you also have period, which go by rho. Okay, there's a line right here that separate the metals on the left side and the non-metal on the right side. Okay. Those should be a good review as well, okay? But that's not our main focus here. Okay, so that's the first part of these chapters. Structure, so know how to count electron, proton, neutron. Know how to calculate neutrons. Okay, by taking the mass number, subtract the atomic number, which is the number of protons. Okay, and be able to figure out the number of electrons for neutral atoms. That's easy. You look up the atomic numbers. But for the positive ion, you subtract, okay, the electron, and for the negative ion, you add the electrons. Depends on the charge. If it's +1, you subtract 1 electron. If it's -1, you add 1 electron. So, for example, sodium plus. Sodium has 11 electrons, so sodium plus, you subtract 1 because it's losing 1 electron, so that's 10 electrons. On the other hand, you have chlorine atoms. Chlorine has 17 electrons, so chlorine minus has 18 electrons because you add 1 electron. All right, so we'll continue with nomenclature, which is actually a good big topic of molecular and ionic compound. Thank you. I'll see you in the next lecture.